Hello everyone. Today we are going to analyze this frame using Kani's method. Before analyzing, let us see the frame one time. In this frame, we have three different parts. In the span AB, we have a uniformly distributed load 9 kN per meter acting for the full span. In the span BC, there is a point load 24 kN acting at a distance of 3 meter from the point B. In the vertical member BD, we have a point load 10 kN. It is acting in the center. Length of AB is 4 meter. Length of BC is 5 meter. Length of CD is 4 meter. The moment of inertia for AB is 3I. The moment of inertia for BC is 2I. The moment of inertia for BD is I. This frame is a non-sway type frame because the fixed support in the point A will not allow any horizontal displacement. Now let us find the fixed end moments. First, let us find them in the span AB. In the span AB, there is a UDL 9 kN per meter. This UDL is acting for the whole span. The formulas for finding the fixed end moments are minus WL square upon 12 and positive WL square upon 12. After applying the values inside the formulas, we are getting MFAB and MFBA. Now let us find the fixed end moments in the span BC. In the span BC, we have a eccentric point load 24 kN. The formulas to find the fixed end moments are minus WAB square upon L square and positive WA square B upon L square. When we apply the values inside the formulas, we are getting MFBC and MFCB. Now let us find the fixed end moments in the column BD. Here there is a point load 10 kN. This point load is acting in the center. The formulas to find the fixed end moments are minus WL upon 8 and positive WL upon 8. When we apply the values inside the formulas, we are getting MFBD and MFDB. We have calculated all of the fixed end moments. In the point C, there will be no movement because it is a simply supported end. So the moment MCB will be 0. In this case, we can release CB and make this analysis easy. For CB, the fixed end moment is 17.28. When we add minus 17.28 with this 17.28, we will get 0. Now we have to give carryover from CB to BC. When we divide minus 17.28 by 2, we will get minus 8.64. Now let us find the adjusted fixed end moments. For AB, BA, BD and DB, there are no changes. For BC, we have to add these two values. After adding, we are getting minus 20.16. In the Kani's method, we have to find the rotation factor. We have to find the rotation factor only in the joints. In this frame, there is only one joint, that is the joint B. In this joint B only, we have to find the rotation factor. To find the rotation factor, we have to calculate the stiffness. Let us see the formulas to find the stiffness. If the fair end is fixed, the formula is 4EI upon L. If the fair end is hinged or with roller support, the formula is 3EI upon L. If the fair end is continuous, the formula is 4EI upon L. From the joint B, we have to find three stiffness values for BA, for BC and for BD. First, let us find for BA. For that, from the joint B, we have to look at the point A. In the point A, there is a fixed support. If the fair end is fixed, the formula for the stiffness is 4EI upon L. The moment of inertia for BA is 3I. So instead of I, we have to apply 3I. Length of BA is 4. Finally, for the stiffness of BA, we are getting 3EI. Now let us find the stiffness for BC. For that, from the joint B, we have to look at the point C. In the point C, there is a hinged support. If the fair end is hinged, the formula for the stiffness is 3EI upon L. For BC, the moment of inertia is 2I. So instead of I, we have to apply 2I. Length of BC is 5 meter. Let us apply that. Finally, for the stiffness of BC, we are getting 1.2 EI. Now let us find the stiffness for BD. For that, from the joint B, we have to look at the point D. In the point D, there is a fixed support. If the fair end is fixed, the formula for the stiffness is 4EI upon L. Length of BD is 4. Let us apply that. Finally, for the stiffness of BD, we are getting EI. Now let us find sigma k. For that, we have to add these three values. After adding these three values, we are getting 5.2 EI. Now let us find the rotation factor. The formula for the rotation factor is minus 1 upon 2 into k upon sigma k. Using the formula, we are getting the rotation factor values. In Kani's method, in the joints, we have to make boxes. In this analysis, there is only one joint, that is the joint B. So in the joint B, we have to make a box. Now let us enter the fixed end moments. We have to be very careful. We have to enter the adjusted fixed end moments. For AB, it is minus 12. For BA, it is 12. For BD, it is minus 5. For BC, it is minus 20.16. For CB, it is 0. For DB, it is 5. In the joint B, we have three fixed end moments, 12, minus 20.16 and minus 5. We have to add these three fixed end moments. When we add, we will get minus 13.16. Now let us enter the rotation factor values. For BA, the rotation factor value is minus 0.2885. For BC, it is minus 0.1154. For BD, it is minus 0.0961. Now we are going to find the rotation contributions. The rotation contributions generally will be available only in the joints. In the joint B, we have three rotation contributions, M-BA, M-BC and M-BD. In the fixed supports, there will be no rotation contribution. In the point C, we have already released MBC, so there will be no rotation contribution. So we know that in the points A, D and C, the rotation contribution is 0. Let us see the formula to find the rotation contribution. Summation of rotation contributions at a fair end plus summation of fixed end moments into rotation factor. In this formula, let us see how to find the summation of rotation contributions at a fair end. M-BA, M-BC and M-BD are located in the point B. For the point B, the fair ends are the point A, the point D and the point C. We know that in these 3 points, the rotation contribution is 0. So, for the summation of rotation contributions at a fair end, we have 0 plus 0 plus 0. The summation of fixed end moments is minus 13.16. So, for M-BA, M-BC and M-BD, the summation of rotation contributions at a fair end plus summation of fixed end moments will be same. Only the rotation factor will be different. The rotation factor for M-BA is minus 0.2885. The rotation factor for M-BC is minus 0.1154. The rotation factor for M-BD is minus 0.0961. After the calculations, we are getting M-BA, M-BC and M-BD. Let us enter the values of M-BA, M-BD and M-BC. In this analysis, we have only one joint, so only one iteration is enough. We don't have to go for the second iteration. Even if we do the second iteration, we will get the same values. Let us see the formula to find the final moments. Fixed end moment plus 2 into rotation contribution at near end plus rotation contribution at fair end. Let us make a table. In the table, first let us enter the members. Then let us enter the fixed end moments. Then let us enter 2 into near end contribution. Then let us enter the fair end contribution. We know that for AB and DB, the near end contribution is 0 because in the fixed supports there will be no contribution. For BA, the near end contribution is 3.7966. For BC, the near end contribution is 1.5187. For BD, the near end contribution is 1.2647. For AB, the fair end is BA. In BA, the contribution is 3.7966. For BA, the fair end is AB. In AB, the contribution is 0. For BC, the fair end is CB. We know that we have already released CB and made it 0. In this case, the contribution in the point C will be 0. For BD, the fair end is DB. In DB, the contribution is 0. For DB, the fair end is BD. In BD, the contribution is 1.2647. We have to be very careful. For CB, we cannot add 2 into near end contribution and fair end contribution because we have already released CB and made it 0. Now let us find the final moments. For that, we have to add these 3 values. After adding, we are getting the moments. In this analysis, we have found all of the moments. For MAB, we got a negative value. That means MAB is acting in the anti-clockwise direction. For MBA, we got a positive value. That means it is acting in the clockwise direction. For MBC, we got a negative value. That means it is acting in the anti-clockwise direction. We know that MCB is 0. For MBD, we got a negative value. That means it is acting in the anti-clockwise direction. For MDB, we got a positive value. That means it is acting in the clockwise direction. Now we are going to find the reactions. First, let us take the span AB and find out the reactions. In the span AB, there are two movements, MAB, which is acting in the anti-clockwise direction, and MBA, which is acting in the clockwise direction. In this span, first I am going to find out RA. For that, I am going to take movement about B. In this case, I am moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. RA is acting towards the point B in the clockwise direction, so it will be positive and the distance is 4 meter, so 4 RA. The UDL is acting in the anti-clockwise direction, so it will be negative. When the UDL comes, we have to multiply with the distance and distance by 2. Then we have two movements. The 8.2 movement is acting in the anti-clockwise direction, so it will be negative. The 19.59 movement is acting in the clockwise direction, so it will be positive. Finally, for RA, we are getting 15.15 kilonewton. Then we can apply the rule sigma V is 0 and find out RB1. Now let us take the span BC and find out the reactions. In the span BC, there is only one movement, that is MBC, which is acting in the anti-clockwise direction. In this span, first I am going to find out RB2. For that, I am going to take movement about C. RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 5 meter, so 5 RB2. The point load 24 kilonewton is acting towards the point C in the anti-clockwise direction, so it will be negative and the distance is 2 meter. Then we have a movement which is acting in the anti-clockwise direction, so it will be negative. After the calculations, we are getting RB2. By applying the rule sigma V is 0, we are getting RC. We have calculated the vertical reaction in the point B 2 times. To find out RB, we have to add RB1 and RB2. After adding, we are getting RB, which is equal to 33.89 kilonewton. Now let us take the column BD and find out the reactions. In BD, there are two movements, MBD, which is acting in the anti-clockwise direction, and MDB, which is acting in the clockwise direction. In this span, first I am going to find out HB. For that, I am going to take moment about D. HB is acting in the clockwise direction, so it will be positive and the distance is 4 meter, so 4 HB. The 10 kilonewton point load is acting in the anti-clockwise direction, so it will be negative and the distance is 2 meter. This movement is acting in the anti-clockwise direction, so it will be negative, and this movement is acting in the clockwise direction, so it will be positive. Finally, we are getting HB. By applying the rule sigma H is 0, we can find out HD. Now let us make the shear force diagram in the spans AB and BC. We have to make this diagram using the vertical loads and the reactions. Now let us make the shear force diagram in the column BD. Using the horizontal load and the reactions, we have to make this diagram. Now we are going to draw the bending moment diagram. First, let us make the free movement diagram. For the free movement diagram, we have to assume every span as a separate simply supported beam. Using these formulas, we can find out these movements and draw this diagram. Now let us make the end movement diagram. Using these movements, we can make this diagram. For making this diagram, we have to see the direction of the arrows and draw. Now let us combine the free movement diagram and the end movement diagram so that we will get the bending moment diagram. Now we are going to end this session. Thank you for watching this video.